I think we are ready to begin. So the
Okay.
speaker today is Ming-Lun Hsieh from National Taiwan University, and he's going to talk about p-adic L functions for U3 cross U2. Thank you.
Okay, thank you very much. And I would like to thank the organizers for inviting me to this talk. And I'm sorry I'm not able to attend this conference in person. Okay, so today I'll talk about p-adic functions, actually a square root of p-adic functions for U3 cross U2. And this is a joint work in progress with Michael Harris and Shansuke Yamana. Okay, so let me begin with some notation. So K will be imaginary quadratic field over Q, and I will fix P to be a prime and a isomorphism between C and the completion of the algebraic closure of QP, CP. And I will assume in this talk that P is always split in K, and split into frac pay times frac pay bar, where pay is the prime induced from this isomorphism iota P. Okay, and I will take a V prime H prime, which is a Hermitian space. Over K with dimension 2. Okay, and H prime is a Hermitian form on V prime, which is, I assume it is positive definite. Okay, and I'll let VH be a degree 3 Hermitian space over K, which is defined by as follows. So V is V prime direct sum K times a vector E, and the quadratic and the Hermitian form H is H prime direct sum H0, which H0, the value of H0 at EE is 1. Okay, so we'll consider unitary groups associated with these quadratic spaces. UV prime and UV. Okay, so this UV prime is U2 in my talk, in my in the title of my talk, and UV is U3. Okay, so these are definite unitary groups. So they are compact at infinity. Definite unitary groups. Okay, and suppose we are given 3 variable Hida families. Fk on UV, K where K is K1, K2, K3. So it's 3 variable and it runs in ZP. And 2 variable Hida family. F prime, K prime. K prime is K1 prime, K2 prime in ZP3. UV prime. Okay, and we can and the M, and we can consider the automorphic representation pi Fk or pi Fk prime on UV and the UV prime generated by FK or FK prime, K prime. Okay, so I haven't really introduced the notion of Hida families on definite unitary groups, which I will recall later. But here just gives you a flavor. So a flavor about these three variable Hida families or two variable Hida families on unitary groups. So you can view it as a collection of automorphic representations on unitary groups parameterized by three tuples or two tuples in ZP. Okay, so and here so but if we want to really get a automorphic representation, then we have to assume for K, K1, K2, K3. So I need to assume this is a dominant condition. So in Z3, and the K prime is the same. Okay, in Z2. Okay, so in the M of this talk is to expand a construction of a 5-variable p-adic function, which interpolates square roots of the central value which I denote by the algebraic part of this. Of this Rankin-Selberg L function. And this is defined to be the central L values of the Rankin-Selberg L function associated with the pi fk and the pi f prime k prime divided by this should be period L1 of adjoining L function of pi fk and L1 adjoining L function of pi f prime k prime. So I will refer this number to be the algebraic part of these central values of Rankin-Selberg L functions. Okay, so to be more precise, we shall construct an analytic function which I denote by theta f prime from 5 copies of ZP valued in CP, such that when we evaluate k prime, so this is 3 digits and 2 digits, the square is equal to this central value times a modified Euler factor. Suggested in Zhen Liu's talk in the morning. So this interpolation holds for KK prime satisfy certain interlacing relation. With the interlacing relation, which also appeared in the talk of Shiling Lan. So this relation is given by as follows: K1 less than or equal to negative K2 prime less than or equal to K2 negative K1 prime to K3. Okay. So this p-adic function interpolate a square root of central values for KK primes with the interlacing relation defined by this star. Okay, so this interlacing relation is closely related to this GGP conjecture, and I will come back at this point later. Okay, and I also need to introduce this modified Euler vector. This EPS. So this modified Euler vector was introduced by Coates in the Pirang, and it can be defined in terms of datum of Galois representation associated with these automorphic representations. So according to works of in this particular setting, Closure, Harris, Taylor, okay, and Garrity. Okay, we can associate. We can associate the Galois representations. Rho pi. So pi is referred to pi fk, pi prime is referred to pi prime fk prime. Okay, and we can associate Galois representations. Rho k, a p-adic Galois representation. Rho pi or rho pi prime from the absolute Galois group of K to GL VK or GL VK prime. Okay, and the dimension of VK is 3. And dimension of VK prime is 2. Okay, such that the L function of this the L function of this Galois representation plus 1 is equal to the L function of pi, and L function of rho pi prime is equal to L function of pi prime. Okay. Furthermore, we also have a description of the Galois representation when restricted to GQP. Okay, so then in particular, there exists a filtration. There exists. Okay, sorry. Then as a GK pay module, a GK pay representation. So this is pay, GK pay representation. Okay. There exist filtrations. So this is by ordinary condition, p-ordinary assumption, because we assume F and F prime are Hida families. So then there exist filtrations. This F3 VK, F2 VK, F1 VK, this VK, and F2 VK prime, F1 VK prime is VK prime. Okay, such that the graded piece, these are sub GK pay representations, and the Hodge-Take weights. These are all Hodge-Take representations, and we can talk about its Hodge-Take weights of each graded piece. Vk is given by ki plus 3 minus I. And this graded piece, Vk prime, is ki prime plus 2 minus I. Or I is 1, 2, 3. I is 1 and 2. Okay, so these ordinary assumptions, by ordinary assumptions, assures affiliations with very explicit Hodge-Take weights. Okay, and then we consider the tensor product representations, VK K prime, to be tensor product representation. Okay, so this has dimension 6. Okay, and we consider a particular submodules inside these 6-dimensional representations. It's defined by F plus. It's defined by F3 VK tensor VK prime plus F2 VK tensor F2 VK prime. Okay, so this is a submodule. This is a GK pay local subspace invariance. This is GK pay invariant subspace. Okay, and the dimension is 3. Okay, so this subspace, this particular invariance subspace is very important. I guess in Schilling's talk, he must have mentioned this is related to the formulation of the local conditions of the Selmer groups related to this p-adic function by Iwasawa main conjecture. Okay, so this the introduction of this subspace is very important. And then with this subspace, we can define the modified order vector. So then we define E pay pi fk let me take a shift as minus 3/2. The reason I put a shift here is because of the shift here. Okay, so this is defined to be the local L factor associated with this subspace. Epsilon. take a dual, okay, and multiply by the local L function of these tensor product representations. Okay. So this is the modified order vectors at pay, and likewise, we can define E pay bar. Okay, and then the modified order vector is the product of these two, E pay and E pay bar. Okay, so let's check my notation. Yeah, that's right. The modified order vector is. Sorry, I should have switched as this. Okay, it's defined to be E pay and E pay bar. Okay, so this is the definition of modified order vector from in terms of the local Galois representations. So this has a degree. This order vector has a this modified order vector has a degree 6 degree 12. Okay, so this is the interpolation, the most important ingredients in the interpolation format: central value, period, and modified order vector. So, and now I would like to expand what do I mean by Hida families on definite unitary groups. So I recall some Hida theory for definite, some notations from Hida theory for definite unitary groups. So basic reference is Garrity thesis, and also Hida's ATA annals paper, where he treated the case for definite quaternion, totally definite quaternion algebras. But Hida's method can be generalized to general compact groups without too much difficulty. Okay, and also if I recall correctly, Garrity also gave a lecture series on Hida theory for definite unitary groups and its application to R equal to T theorems in Pune in 8 years ago. Okay, so there should be some lecture notes on this subject. Okay, so I just recall the notation I need for this talk here. So I'll let G to be UV. VH is a definite Hermitian space. Of dimension D. Okay, and I fix an isomorphism because P splits in K, so I fix an isomorphism of GQP. The isomorphism actually just take a projection on along this pay direction. So GQP isomorphic to GL3 QP. GLD, sorry, GLD. Okay, And I consider in Iwasawa algebra lambda D TD. Iwasawa algebra, D variable Iwasawa algebra, and O is some finite flat extension of ZP. Okay, and I fix an open compact subgroup. Let me use KLK GAF. Okay, such that the P component of this open compact subgroup is precisely GLDZP. Okay, and then for each n positive greater than or equal to 0, I defined Kn to be G in K iota P G. The P component is congruent to upper triangular unipotent subgroup modular P to the n. Okay, and I'll consider the following per finite finite sets. So X infinity G is defined by the inverse limit n GQ GAF quotient by is Kn. Okay, so this inverse limit is taken with respect to the natural projection, so which are denoted by this. So this is natural projection. So this is natural projection. Projection map. Okay, so so this space has a action has action by ZP cross to the D. So namely, you take a X, you take T1 to, you can take multiplication. So namely, if you take a class, okay. So has action by what do I say? So by X times D1 dt. So it's just multiplication. By this iota, this identification between KP and the GLDZP. So inverse TD. Okay, defined by this, and TI in ZP equals. Okay, so it has action of this torus, D copies of p-adic torus. Okay, and then I can introduce non-dyadic forms on this space. So S, so this is definitions of non-dyadic forms. So these are so this is space functions, space of all functions f from this set, this per finite set, to values in lambda d. and I require is a continuous with respect to perfect topologies on both sides. And I also need, this is the torus X on this via particular characters. Okay, so where Tx is defined to be, so X is a variable. The T is an element in ZP course. So this is defined by 1 plus X, the power series, 1 plus X to the log. It was our log of this T over it was our log of this gamma 0. So gamma 0 will be 1 plus P, 1 plus 2P in this talk. Okay. Okay, so this is the definition of non-dyadic forms, and we can have Heck operators X on these forms. So in particular, I can introduce. I will introduce the UP operators. So I'll introduce alpha I is defined to be P I 0 0 I D minus I. So this is an element in GL D QP. Okay, and I defined the UP operators associated with this alpha I. X on F is defined to be sum of X P I star 0 I D minus I. And star runs over I cross D minus I matrices with the coefficient with values in FP. Okay, so this is F in SG lambda D. So this and then I define UP operator is a product of these UP operators. So this gives us an element in the endomorphism. In the endomorphism of SG lambda of the endomorphism on these non-dyadic forms, and then we can define the ordinary projection. Ordinary project Hida's ordinary idempotent as defined by to be the inverse. To be the limit to limit UP to the n factorial as usual. So and this will converge to an endomorphism inside non-dyadic space of non-dyadic forms. Okay, and then finally I can define the ordinary forms on ordinary non-dyadic forms in this way. So this is a definition. So this is the space of ordinary non-dyadic forms. Okay, and then it's proved in David Garrity thesis that this space is free of finite rank over lambda D, and also he also proved control theorem. Okay, but once again, these proofs all boils down to Hida's ATA annals paper. Okay, so in particular, and we have specialization. So namely, given F inside this space, okay, and K is the B tuples in Z and the K1, KD. Then we can consider its specialization. It's defined by F evaluates at gamma 0 K1 minus K1 is 1, gamma 0 K2 minus 1, blah, blah, KD minus 1. Okay, so this FK is a functions on this space. This is a complex subgroup. You remove the P part. Actually K1. Sorry, this is K1. Sorry. No. Remove the P part and the values in CP. Okay, and FK is actually the p-adic avatar of a vector valued automorphic form. Which I denote by phi fk. So it's an automorphic form. It's a function on GA, left invariant by GQ, right invariant by K, and the values at LKC. So LK is the algebraic representation of GLDC of extreme weight negative K. Okay, so and then so here I did not explain because of time. I did not explain what do I mean by p-adic avatar. Okay, but actually so they have so FK and the phi FK has a very simple relation. So but has a simple relation, but it's rather complicated to write it down here. So I just say it's a p-adic avatar of a vector valued automorphic forms. And I pick sorry, vector value, so I should use this. Okay, and I choose L negative K inside dual. So this is dual. So this is a vector of highest weight. So actually this is minimal weight. And this is the highest weight. Highest weight is negative K. So this is minimal weight is K. Highest weight for negative K. Okay. And so this is dual. And then phi fk G is defined to be a pair with this highest weight. So this is, and then this is automorphic form. In the usual sense. Automorphic on unitary group UV. And now let pi fk be the automorphic representation generated by phi fk. Okay, so this is my notation about Hida families on unitary on definite unitary groups. Okay, so and with this notation, now I can explain the construction of the p-adic function. Okay, so the idea is to take Hida families on UV and another Hida families on UV prime, and then their functions on X. So F. So now F is okay. So now I take F and the F prime be two Hida families on UV cross UV prime. Okay, so their functions, they can view it as a functions on X infinity. So X infinity cross X infinity values in lambda 3 tensor with lambda 2. So and the X infinity is this UV. Okay, so there are functions on this product of two per-finite sets. Okay, values in Iwasawa algebras. So the idea is to construct non-dyadic diagonal cycle in this product space. Okay, so to be more precise, I'll define delta n plus for each n. We define lambda n plus is defined by this set. P2n PnB 1 0 0 1 x 0 1 negative P2n. Okay, so this iota here is the natural inclusion from UV. Okay, so we define a formal combinations of elements in X infinity cross. So we can view this as an element in Xn cross Xn prime. Okay, so Xn is just I forgot to give the name. It's just this. Okay. So we define so a formal combinations of points in Xn. Okay, and the lemma says. So also you can regard this as a so it's a Picard of Xn cross Xn prime. So the lemma is the norm compatibility. So namely, when you take a projection from Xn plus 1 to from delta n plus 1 dagger and you take projection onto xn cross xn prime, then this is equal to up tensor up. Okay, so this can be checked just by definition. So with this lemma, we can introduce non-dyadic diagonal cycles. It's defined by inverse limit of up. E odd tensor E odd sheet in this diagonal cycle. So this is an element. So this is an element inside x infinity equals x prime infinity. Then we can define. Then we can define the p-adic function. Theta by the following, very simple. You just take this formula. You just evaluate at this non-dyadic diagonal cycles, and this gives us an element inside lambda 3 tensor product with lambda 2 over O, and this is 5 variable Iwasawa algebras. Okay, and finally, I would like to. So this is a this is an element in Iwasawa algebra, but and now I need to expand its relation to L values. So it would be convenient to introduce the following notations. So I introduce k prime. So this is defined to be theta ff prime evaluate gamma 0 k1 minus 1 gamma 0 k3 minus 1 gamma 0 k2 prime minus 1. Okay, so now I'll talk about the interpolation of this theta elements. So the first step is to express theta ff prime as a period integral over uv prime. And the second step is to relate this period integral to central L values. Via the Ikeda, Ichino conjecture for unitary groups. So actually, we need the Ikeda Ichino conjecture for cuspidal tempered representations on unitary groups, which has been established by the work of Buzzard Places and Yifeng Liu and Wei Zhang and Xinwen Zhu for the stable case, and also Buzzard Places and Chodernat and Zido for the remaining endoscopy case. So now it's not conjecture, it's a theory, and proved by followed by many people's work now. So we can use this theorem to relate a period integral to central L values. Okay, so for the first step, we need to use the interlacing relation. So the interlacing relation star tells us there exists a non-zero element inside LK due tensor LK prime due Z and fixed by G prime Q. Okay, so there's a invariant element inside this space, and then we can make this delta K prime very explicit and prove the following proposition: theta 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 KK prime actually is a local integral of these automorphic forms. Okay, so this is a period integral that we want to study, and the proof of this proposition is based on is a analog of the proof uses analog of a Ming-Lun Hsieh. Okay, in this definite setting, so you can for this Ming-Lun Hsieh, a reference is given is Kitagawa. It's a 94 paper, so you can check. It's a Lemma 4.6. So basically, in this Kitagawa's case, it's a two-variable p-adic function associated with modular forms. And he need to know modular symbol for different the congruencies between different critical values. So here we roughly we have to do the same thing. So so we have to. So actually, we prove this by congruencies on both sides, modular a arbitrary high power p. Okay, so this is a Ming-Lun Hsieh, so which allows us to relate this theta element to period integral. Okay, and then for the second part, we have to use Ichino Ikeda conjecture. The Ichino Ikeda conjecture, as mentioned in yesterday's Wei Zhang's talk, it expresses the square of period integral in terms of central L values and a product of local zeta integrals. Involving matrix coefficients of test vectors in these representations, and the calculation. So according to this Ikeda-Ichino's conjecture, the interpolation formula boils down to explicit calculation of these local zeta integrals, and the calculation of these local integrals at unramified places was done by Neil Harris. So in our work, the most important contribution in our work is to carry out this calculation at the p-adic place, which is similar item in Zheng Liu's talk. So p-adic integral is it's a new new ingredient in this work. And as also alluded in Zhenliu's talk, eventually we have to use local zeta integrals. And so I just say for p-adic local zeta integral, for p-adic zeta integrals. For p-adic zeta integral. So we use Lapi's result, which tells us this local zeta integral is a product of two Rankin-Selberg integrals for GO3 cross GO2. Okay, and then we use local functional equations to use local functional equation to change the Rankin-Selberg integrals for GO3 cross GO2 to GO3 cross GO1. Okay, and which can be evaluated explicitly. So this modified order factor actually appears from the local functional equations. So this is the place. Also, Zhenliu also pointed this out. This is the place we got modified order factor. At P. Okay, so this is roughly a sketch of our construction. So there are some details about choice of test vector at the ramified places. It's another difficulty. So finally, I still have 2 minutes. Finally, I want just quickly give a concluding remark. So so actually, if you check as mentioned in Shilin Lai's talk, there are 10 interlacing relations. So for this U3 cross U2, for automorphization on U3 cross U2, and so we just work out one of them, and so which means we have 10 p-adic functions for U3 cross U2 with 10 different periods and different local conditions as Selma groups. Okay, and this interlacing relation can be best described in terms of Hertz-Schwencher parameters. So for pi k infinity and pi k prime infinity. So it's given by a tuple of 3 integers, 3 numbers, and half integers. So in our case, it's 1 minus k1, negative k2, negative 1, negative 8 k3. And for mu1, mu2, this is just a k2 plus 1/2, and k1 prime minus 1/2. Okay, and then the interlacing relation can be rephrased as lambda 1 greater than mu1 greater than lambda 2 greater than mu2 greater than lambda 3. Okay. So, and we can if we consider a different interlacing relation like this, greater than mu1 greater than lambda 2 greater than lambda 3 greater than lambda 2. Okay, then we have to transfer pi fk and pi fk prime to quasi-split U21 cross U11. Okay, and in which case we also obtain a similar result by a similar construction of p-adic functions by using Rankin-Selberg method. So we have to deal with we have to interpolate Fourier Jacobi coefficients of Hida families on U21. Okay, so okay, so thank you. I'll stop here. Thank you.
Thank you very much. Are there any questions or comments?
It's lunchtime.
Hello. So
Hi.
my question is, maybe I didn't understand really this interrelation. So my
Interlacing
question
relation.
is, so if you replace, so you have two families, two Hida families. So if you replace just, I don't know, which is easier, you one to other families like Coleman family or some other period, is this much more difficult or?
In the compact case, I think it's the same.
Oh, really?
Yeah, in the compact case, so as long as you, I think in compact case for common family, we can play the same game. And indeed, there is a work by, but very vague. You know, there's a work by Cerveso and Greenberg.
I see.
Yeah, and they consider this kind of thing. So they construct this p-adic function associated with compact group as a distribution. But they did not, if I recall correctly, they did not specify the growth order of the distribution. Yeah.
You can even change both of them to Coleman family.
Yes, at least for compact case.
Yeah. Okay.
Yeah, the interlacing, if the interlacing with the star. Yeah, but with different interlacing relation, it's more difficult. Yeah, because we have to use different unitary groups. And yeah.
Oh, okay. Definite case.
Yeah, definite case is easier. It's easier.
Okay. Thanks.
Yeah, no problem. Yeah.
We also have one question in the chat from.
Okay. Let me see.
So if the local zeta
Integrals are non-zero. Yes, so we have to choose the good test vectors, and we can always choose a test vector such that the local zeta integrals are non-zero, but it may be the optimal one, because we may lose local factors at these places. Yeah, so the answer is yes. We know these local zeta integrals are non-zero. Yeah, but we yet find an optimal test vectors about the value of local zeta integrals, in particular at ramified places. Yeah. Okay.
I think I have a question. So why do you restrict to U3 cross U2 instead of UN cross UN plus 1?
Yes, yeah. All construction can be generalized to UN cross UN minus 1 without any difficulty. Yeah, just because I need to introduce more notations in that situation. Yes. So I'm pretty sure okay. So there will be one slight difficulty, namely I have to make this the proof of this proposition, because I use explicit form of this delta KK prime. Yeah, maybe in higher rank case, but I think it's still doable. Yeah, you're right. Everything can be generalized to UN cross UN minus 1 without too much difficulty. Yeah. Thank you. Yeah.
Any further questions or comments? Doesn't seem to be the case, so let's thank the speaker again.
Thank you very much, and enjoy the lunch.
We now have a lunch break and we resume at 4 p.m.
Okay, thank you.